to have Professor George Smoot give us a talk this morning on LIGO events as gravitational events, magnified stellar events, black hole merger, and cosmology.
All right. So thank you. This is just before a model, but in a different kind of model. And I'm going to give you a summary in the first couple of slides, what the main essence of the model is, and then go through the arguments, which came from ideas, the stuff that I was working on a year ago. In fact, I gave a talk here at 1.05 years ago about this, and I'll show you a couple of slides from it. The basic idea, the basic thing I want to say is we did a preprint just a little over a week ago, and this morning a slightly edited updated version to collect typos, so it should have appeared on the archive. And my collaborators are Tom Broadhurst and Jose Maria Diega, so you can actually read more, although I'm going to show you more stuff here than we actually could put in the paper. Or we did put in the paper, we may eventually put it. The basic issue here is the chirp mass that you observe and the chirp mass that's real are scaled by a factor of 1 plus z. And the distance at which the luminosity distance that LIGO, Virgo report is actually the true luminosity distance divided by the square root of magnification. So those are the relevant things, that there is no unique determination of the z of the objects they're seeing, given if there is gravitational lensing. And now there are lots of arguments about why there isn't gravitational lensing, and I'll come to that in a second. So I'm just going to say it again. The gravity, if you make things in terms of mass and distance, scales completely. So you can't tell where a thing is from, because if you put smaller masses at a larger redshift, they'll look like larger mass at a small redshift. Just scaling by the 1 plus z factor. The other is the luminosity distance reported by LIGO is the actual luminosity distance divided by the square root of the magnification. Right? So that's just a picture. That's an example of a wave, a gravity wave coming from a chirp event with different phases and angular inclinations, and with gravitational lensing, and you don't see them apart because the wavelengths of the gravity waves you're talking about are you're talking about frequencies that are anywhere between 50 to 100 hertz. So you're talking about things that are fractions of a light second, and you're going to see, we think most of the lensing is done by galaxies. And so the scales are such that you can treat it as geometrical optics, and things go fine. Later, John will be giving a talk, and he'll have, oh, you're not going to talk about that? Okay, you change your topics. Okay, so it's the fact that gravity is just scalable that lets you realize you don't, unless you know the redshift, you don't know the mass of what's going on. You need an independent measure of the redshift. Now, that maybe sets up David, or not set up David for his next talk. Okay, so here's the rough numbers. I have a plot over here on the left of the optical depth for magnification 10 or greater as a function of redshift. And you can see that by the time you get to redshift 1 and 2, you're roughly at 10 to the minus 4. And this is part of the argument people have why events aren't lensed, but they don't take into account other factors, right? So you can calculate this lensing to see it's on roughly the right scale. That is, lensing of any element in the universe is going to be proportional to its omega. In case of galaxies, that's roughly 1%. And the probability of lensing greater than magnification mu is essentially 1 over mu squared. So that gives you 10 to the minus 4, but not when you're in close, only out when you're in cosmological distance, when you're scaling across a lot of the mass of the universe. So those are the relevant things. Okay, so if you say, well, it's 10 to the minus 4, you take any random event, 10 to the minus 4 to be lensed, that means 10 to the minus 4 of the LIGO event should be lensed. But that's not correct. And that's because if you increase the distance by a factor of 10, you increase the volume you're looking at by a factor of 1,000. If you go out to a redshift of 2, going to 1, increases you by the factor of 1,000. Going out the redshift of 2 gives you another factor of 5 on top of that. And so suddenly your 10 to the minus 4 times 1,000 or 5,000 gets you in the 10% range for gravitational lensing, just right away. And now the question is, where are the binary pairs that are converging? Where are they converging? What's the stellar evolution rate? What's in this model, because these are stellar mass black holes. What's the stellar evolution rate? What's the merger time? How does that work out to? You can fairly straightforwardly get a factor of 10 to 100, depending on what you think about the binary, black hole formation and evolution rate. So you'll see. And so that's also has to do with the mass function and the individual spacing at the beginning, because that tells you how long it takes to go down. Normally, when you look at this, you'll get roughly 10 to the 8th years. You'll come back to that later. And I also claim this depends very strongly on the situation of the observing run of LIGO Virgo, given its configuration and its data analysis criteria. That if LIGO starts operating closer to its design sensitivity and they change the criteria a little bit, the lensing will go back to 10% from the 50% that our model claims that exists now. That is half of the gravity wave events I claimed are strongly lensed. Now, the rest of the talk is about the details, which is where all the devil is, right? Okay, so here's the sort of current state-of-the-art plot. I hope you can see it. It's sort of like, so those blue things up there are the LIGO black hole plotted as a function approximately of time and aesthetic ability and mass, and you can see the things that merge in their mass, the first ones and so forth, they detected. And then in purple are the known black holes measured from our galaxy and from our local group of galaxies, right? And then recently, neutron stars were added because this is the graveyard. This was done for All Saints' Day or Halloween. This plot came out about that time. Okay, so here's the slide I presented 1.05 years ago in the original room we're in. And the question that I was asking at the time, is there a new population of black holes? Because what you see in the data appear to be these very massive black holes. And are they a new population, or is it something else? And I said I thought there were 3 possible things. There's an extended stellar population, and it means you had to make very successful massive stellar supernova or fail supernova. That is, supernova that completely fall back and never become supernova. They just, you essentially just make a black hole out of the star. Or some kind of strange population, 3 stars, the first generation of stars, that form in the nice binary situation and give you the right time scale. You need 10 to the 10th years as opposed to 10 to the 8th years for the merger, right? The other question that caught my attention, and I was thinking about at the time of this talk, could these be primordial black holes that is produced in the very early universe, and could they be the dark matter? And I'll talk about that briefly, and the question is how they come from, and so forth. So I don't have slides about that, I'll see it. And then, being this is astronomy, so for those of you who aren't astronomers, astronomy is the only science I know in which we name errors after people, like the Malmquist bias or whatever it is. And the fact is there are a known set of errors and biasing. And my claim is that there is a very strong set of selections. And for the gravitational wave detectors, they're about maximal. It's just an accident that things fall in the right range. The neutron star and neutron star mergers are going to move into approximately that range in this next set, but we'll see. And your prediction will be that you could have made before was that 10% of the neutron star mergers will be strongly lensed too, but we'll see, okay? So let's go forward with that. So the model I have now focuses on this, but I went through thinking about those others first, and I expected that some of my Japanese colleagues here were going to be defending the extended stellar population a little more than you did. But so I didn't actually put the material in about that. Okay, so I looked at the question of black holes. I wasn't the only one that thought, well, this is cool. If we need primordial black holes, why don't we make the dark matter out of the two? And so this is a nice review by Bernard, Florian Kugel, and Mario Sennett, set what the limits were. And I said, all right, let's just set in some black holes for distribution, because this is a spike distribution. That is, what's the limit for a delta function? And what if I just make something that's at 10% of the dark matter, but I spread it over 10 decades or whatever? Can I make the sum? And the answer turns out to be no. And but at the time, I was encouraged and say, all right, we can make primordial black holes from running mass inflation, from curvatons. We can do a lot of stuff, and you can squeeze it in there. And there's this nice little window, because you want to make these guys peak up around 30 solar masses, given the data that existed a year ago. Okay. So the problem with that, so then I spent a bunch of time looking very carefully at these limits. And these limits, although expressed as delta function limits, are actually broad mass limits, and it's complicated to turn them back into the right sort of limits. At the same time, the Japanese group, using Subaru, started blocking out the stuff around 10 to the minus 7, because there were a series of papers by certain people who wanted to put primordial black holes in it at 10 to the minus 7 solar masses. And so I worked for a long time. Actually, Razi Amani did most of the work with Razi Amani to go through very carefully all the observations and all the limits that people had and understand what's going on. And some of them, as with any case when people do limits, there are weaknesses and ways to get around them. But when you look at it, it turns out not to be so much the case. So in the end, instead of wasting all our work, we ended up making a paper on the observation constraint on the primordial curvature power spectrum. That is how it's measured with the CMB, how it's measured with large-scale structure, and then extending it with black holes, primordial black hole, limits on primordial black holes, all the way down to the Planck scale. So you can go from the horizon to the Planck length and set limits and so forth. Now, the thing that we found out is that there's no way, if you stretch things as hard as you can, there's no way you can get to more than 10% of the dark matter being primordial black holes. And generally, it's just a few percent, the most you could do at the time. But in that case, you need something else to make the dark matter. And if that turns out to be WIMPs, there should be these failed black holes called ultracompact massive halo objects. And they should show up. They get made a little later, but out of the original fluctuations, they get made later. And they should show up. And you can see them in neutrinos, like an ice cube. So when there are limits against that, you see it in gamma rays if there are annihilations going on. You can see it in pulsar timing, that is time delay. You don't see them. And so that puts a limit that's much tighter, that gets you down below 10 to the minus 6 if you happen to be in the range we're talking about. Just happens to peak there, and that kind of situation. So that becomes relevant to your statement that you need to get to 10 to the minus 3. If you don't have at least 10 to the minus 3, you're having a more difficulty doing that. It doesn't mean you can't make some more. There are some other new limits coming in. There's a nice review paper on primordial black holes and perspectives, if they didn't quote our paper, where they've gone and looked at the sort of more massive black holes in this range and looked at the effects that they would show on the CMB and X-rays and radios and so forth. And you run into the situation where it's hard to get above 1%. You still have this window observationally at 10 to the minus 3, right? I don't find it as pretty to have a universe that has dark matter and then it has 10 to the minus 3 dark matter made out of primordial black holes, but it's still conceivable. There's a secondary problem, which you referred to indirectly, which is you need to make the black holes in groups. You have to make them not just a pair with the right separation. You have to have the third one in order to get the angular momentum to get the orbits in order to make things work out. That means you have to have a non-Gaussianity that couples a non-local non-Gaussianity. You have to couple the physical scale of the separation of the black holes with the perturbations that cause the black holes. Those two have to be coupled. If you're making from primordial perturbations from something like inflation, it gets trickier, and that's the thing that our limits here make more difficult, because what you're saying is you have down at 10 to the minus 6 or lower, you have the primordial perturbations, which are some kind of a Gaussian distribution. Then you have nothing, you have way down, and then out here at 10 to the way out here at the total mass, a tiny fraction, the 10⁻⁹ of them, little Gaussian peak. It starts off at a third of a perturbation and 6 up. So this didn't appeal to me anymore, not the way it did a year ago, before I started trying to do the studies of what's happening. It doesn't mean it can't be true. I just believe you have to stretch this model harder than the error and observation model, right? So that's whatever it is. Okay, so back to one of the things that I presented at that time. There was a nice paper here from this group where they made a compilation of all the published black holes, and this purple is the Milky Way black holes. These, I don't know what color this is, brownish. Those are the Large Imaginary Cloud, and those are the 3 gravity wave events that exist at that time, because they're picking the heaviest mass out of the 2 masses, right? Because in these other cases, they aren't black hole, they're something else. And so you look at the distribution, and you look at what they claimed was the conventional stellar theory, as opposed to the Japanese group theory that has a longer tail. And it has that similar kind of shape. It's not so far from a log normal, which is also what you get from axion cosmology and so on. So the log normal will come again. So the question that I had looking at this was, there's a selection effect. Obviously, you don't see the low mass black holes when they're out past the edge of the galaxy, right? And you don't see the gravity waves unless they're further out. What kind of a bias? And the efficiency for seeing these has got to grow at least as the mass squared for these guys out here, because of the way the trigger is done. Okay, so that's the first part of it. So the Japanese group, okay, well, I'm sorry if I spelled names wrong. They had a couple slides that they had out at the time saying, where could these guys come from? They could come from early black holes that take 10 to the 10th years before they merge, or they could come from later produced black holes that take the order of 10 to the 9th or 10 to the 8th years, right? So that's the kind of a thinking that we had about a year ago, right? So the Japanese link was to say, okay, it's population 3 binaries. They're made, half of the binaries and half of the stars in population 3 are binaries, and they're far enough apart that when they make these supermassive black holes, they stay in those distances apart, and it just takes this the right amount of time. And what you're going to see is these first events don't go off until way down here. I mean, there's no events. You should have been able to see them up to here, but you don't see them until they get close, right? That's one of the things that's the hint about this. But anyway, I'm hoping some of the Japanese here will defend their argument about this as a potential model. I think it also has to be stretched in order to make it work. But so does everything else. So here is the now existing observed black hole mass plot without any efficiencies into account. This is just the plot of the masses of all the known. Okay, and so to make up this model, I get rid of all the ones from gravity waves, right? And there might be one event here or might not. It's pretty close to this edge, so it's hinted. And then I say, let's fit models to this. Gaussian, log normal 1, and log normal wide, right? And you can see Gaussian doesn't quite fit, but log normal and log normal wide, right? Here's log normal and log normal wide do kind of fit, right? So that's sort of reasonable. Go back to the original stellar evolution models. This is the kind of distribution they're expecting you to see. So this is what we're going to use in our model. This is what I proposed to Tom and Jose Maria, that we use this kind of model as our model of what the mass function of black hole binaries are, and work from that and see what we come out of it. Okay, so this is the same thing. We're going to assume the mass distribution has the same mass distribution as the galactic black hole mass distribution. All right, I'm sorry about this plot. It works fine on my computer, but it doesn't seem to work on this computer. There's 2 plots in here. This guy and this guy are the same. And this shows you a plot, which is usually the plot people use to argue that the LIGO events are not gravitationally lensed. because they say, look, this gets up here to the, to the 1,000 level, and this guy's down here at the 10 level. But this is DNDZ versus, for a redshift of 0.01 to 0.1, and then from 0.1 to 2, right? So there's a huge difference because this is a log, and if this was DND log Z, you would see this gets boosted up by a factor of 1,000, and so you're in the ball game. And you can also think about saying, what if you put in the stellar formation rate and multiply by the stellar formation rate, which peaks at about redshift of 2, and say the time between the formation, the star formation, and the black hole mergers is relatively short, you'll get a distribution that looks like that. So you're getting up in the right ball game when you realize you get to multiply it by this big factor because this is a 10th compared to 1, and it's a cube or a square depending on how you're doing the thing. So we can, this is sort of a little cleaner version of that. This is a plot that shows in blue the not lensed and in red the lens, but still a DNDZ. These were ones we made up and we're passing back to ourselves because I didn't have time to get a whole set made for this talk, but sort of using what we were using at the time. And you can see then whether we use the Gaussian or the log normal changes a little bit about the reach of LIGO, because if you have this long tail, you're going to have a few more massive events, which lets LIGO see a little further, right? That's the kind of issue. And again, you see the same thing where this is down low, but you're going to get to multiply it by the ratio of the volumes, right? And so you have this, and your evolution function. Okay, so now here's the bad news for our model. Here's a plot that if you have a chirp mass of 8, what do you need in order to get a signal noise of 10? What magnification do we need as a function of z? And the answer is when you're down to no redshift, you don't need any magnification, but you need a magnification that gets to 10 by the time you get to about a redshift of 0.3, and you need a magnification of 100, because it goes as the square root, by the time you get to a redshift near 1. Okay, so now instead of having 10 to the minus 4, it's 10 to the minus 6 because it's going as mu squared. Okay, so I need that extra factor of 10 from someplace. And it turns out it's there, but you have to look for it. Okay, so one of the places you can look is the star formation rate, or you can modify and pick up another factor of 10. You get a factor of 10 from the normal star formation rate, but you can get another factor of 10 depending on what you do for your model of how binary stars form and how binary black holes form. So it just depends on how daring you want to be. We tried different things to see how much trouble we had to go to in order to make things work. Okay, so again, this is just a couple formulas for you to remember. The strain you get is essentially proportional to the chirp mass to the 5/3 power. The frequencies you're seeing times a function of angles times a function of the phase angle of the orbiting around, divided by this luminosity distance d, which is the apparent luminosity distance, not the true luminosity distance, right? And the masses are just scaled by 1 plus z, right? So our problem is we need to get out to a z of 1 so that 1 plus z is 2 in order to drop these 30 solar masses down to 15 and have it be reasonable. So you need the huge magnification. So this is where Roger should be rubbing his head and going, it's going to happen, isn't going to happen, right? Okay, and so here's the formula with the mu in it and the information about the angular sensitivity. This becomes relevant to say the next talk when you talk about how many gravity wave detectors do you need to have in order to tie down the distance better. And there's phase angles and antenna sensitivity angles that are an issue. Okay, so this is just more about how you do the redshift of the phase mass. And I assume this will be online, so I won't go through it. Okay, so here's one of the early plots. These triangles are the observed events, the 6 observed events of LIGO Virgo. And the red squares are 10-year simulated events using our model. And so you can see the signal to noise 10 threshold coming up as a function of the redshift in the observer's frame as the observer interprets it. And the observer gets that redshift by taking its apparent luminosity distance and scaling that using lambda CDM. And you can see these are the guys that come. And what you should have is you should have that log normal mass distribution, plus you should have the lensed events. Now, I have plots later where you'll see the lens events in color and the unlensed ones in black and white. Okay, so this is the first one, and you can see there's something unusual about 3 of the events, and there's something very normal about 3 of the events in terms of what you would expect if you were just having a few events from LIGO. Okay, so here's the plot that has both the error bars. You notice the error bar in the distance is quite large, and it's worse for the events that have low signal noise, but also that have 2 out of the 3 detectors and so forth. And that's because you don't have the angles, so you don't know, you have this quadrupole antenna sensitivity, you don't know exactly where it's pointing, you know, because you have this huge line where it might have come from, and you don't have the signal noise so well. So you can see the masses, you can see the 3 events. You see in black the ones that essentially have a magnification of 1, and you see in the other colors the various magnification, you know, up to 100 here, 500, 2,000, right? And so that's our Monte Carlo of 10 years. If that run last year had run for 10 years instead of for 1 year, well, how many events, you know, those 2 observing you, what that plot should look like. And this is the inferred chirp mass. So there's a 1 plus z, and this is the inferred luminosity distance. It again has a square root of magnification that I have to put into it. Okay, so again, look at the magnifications. You can, in the end, when we go through the stuff, it's elliptical galaxies that provide a lot of the power for this, because if you need the very high magnifications, elliptical galaxies have the caustics and so forth to do it. And so you can do Navarro, Frank White, and the singular isothermal or the soft and isothermal spheres, and you do these different plots. You do lambda CDM, you do ray tracing and other things. This is the prediction where you're going to 10 to the minus 4 and 10 to the minus 6 for the probabilities that any one random event. But we are not picking these events at random. We're picking these events based on the fact that their strain observed is very high. Okay, so if you look at these first events at a redshift of 0.1, if we want them to be at a redshift of about 1, we need a magnification of about 200 for those particular events. If we want to take the guys that are roughly at 0.2 and put them at z equals 1, we need a magnification of about 45. So that's the kind of scaling we have to do. And if you do find them magnified by that, you would see that their rest masses are shifted down by a factor of 1.8 and 1.7 respectively. That's the kind of scale that you're talking about. And I picked these because these were from a separate article. So those people did the calculation independent of us, but it's pretty easy calculation. It's 1 plus z1 over 1 plus z2, whichever z's you're estimating at. Okay, so here's one of our early plots that was something that caught our eye and made us think work should keep going on. So if you plot the volume out to which the event is detected divided by the maximum volume it can be detected, you expect on average for the events to be at a volume of 0.7. But in fact, you will notice those 3 high mass events are all below about 4/10 of a volume. That is, they're much closer than you would be expecting. So in order for that to happen, they either have to be something like being magnified, or you have to put the black holes just far enough apart that they barely, they only start coalescing right at the last moment here. LIGO is triple lucky, right? They got to see an event before they turned on practically. They got to see great events, and they happen to be just late enough in the universe that these guys are merging, right? That doesn't seem like it's clearly going to come out. Okay, and you look at the ones that we say are more like normal events, they're all out here at the volume of a half and above, right? And they're near 0.7 on average, which is the kind of thing you would expect. Okay, so.
What's the difference between the triangle and the red square?
The red squares are the simulations, and the triangles are the actual observations. Sorry, this is early. I mean, it's not that. I mean, we worked on this. That's just like a month ago, and then, we actually evolved as we. This is a month before the paper is done. This is where we're starting to be convinced that maybe there's something real here, and we should be looking at it. Okay, so we made another plot like this. What would you expect if you had the stellar black hole population and you had no lensing? What would the inferred distance versus inferred mass look like? It would look like this. You should have this log normal distribution, and you have the cutoff. You're cutting across the log normal distribution out here in terms of triggering. And so you don't see many events, just like in the plot, you don't see so many events above a mass of 20. You don't see any in that curve because the probability in 10 years of getting one about that is not very high. That's assuming there isn't a second population, right? So that's the question is there a second population? What does it come from? Is it from the population 3 stars or primordial black holes, or is it gravitational lensing? So our model is it's gravitational lensing. Okay, so here's a plot that shows you the kind of thing you would get in redshift versus the Monte Carlo lensed, and the actual data points, right? And so that's the kind of thing. But now you have to look at the model and say how realistic is this lensing model and so forth. And my claim is it's reasonable, but you're tweaking things a little, but it's not too severe. Okay, and here's more plots. I think this is one before the one that we actually posted, so it's a little different looking. But if you just try and put in, 10 years of 8.5, a chirp mass that's around 8, and put it in here, you end up with this distribution for the lens events and so forth. So you can get higher mass events, but that's the kind of thing you're seeing. So, all right, now if we had a lot of money and a lot of long-lived grad students, you could run for 100 years and you get this distribution, and you can see now the unlensed guys, the basically unlensed guys, because everything's lensed a little bit, showing up along this curve, and then you see the gravitational lens guys in this kind of situation. And you see, in order to get that event, you had to go to high magnification, right? Given this model where you're basically cutting off at 20 mass black hole, 20 solar mass black hole. Okay, and this is more plots trying different scenarios with Gaussian and monochromatic log normal. What kind of things can you get, and so forth. So the redshifted Church mass, if the parent mass distribution is narrow, and there's strong evolution of the binary, so they don't lag behind the formation, then the high magnification, these guys can come from high magnification, right? This bag is on sale, by the way, but just had my slides were so boring, it's whatever, right? And so this is what we are claiming is most consistent with the observed LIGO events detected so far. It's up to other people to put up better models, but there's going to be data coming in that's going to differentiate this model from other models fairly soon. And there's some data in the can that might be able to do some of the discrimination already. So we can predict in the future that we're going to see similar distribution to our Monte Carlo. And it's possible at some point 2 images of the same event could occur. So if you're a LIGO Virgo collaboration, you got to be watching to see if you have an event, and if you have another event. Now that's one of the questions. So this is not in our paper. I mean, this statement's in our paper, but the calculations are not in our paper yet because we're still working on it. You can look at the magnification versus time delay that you would expect for certain kinds of lensing events, right? Now, if you want a magnification of 100, you're going to end up with a short time delay because a high magnifications mean you're near a caustic line, and that means there'll be on the other side of the caustic another one. The time delay between those won't be so great. The first guy, in general, the first guy will be the brightest guy, and the second guy will be not. But it doesn't have to be that way. It can be inverted, so the time delay can go either side depending on the structure of the mass you put up. Okay, so here's the critical thing. So we focused on, at least I've been focusing on elliptical lenses, and that's because elliptical lenses have all kinds of extra cool things. And Roger knows this. I have one plot from one of the things you did in here. If you look at the caustic lines, it's not just a simple thing where you get in a straight line and you get the Einstein ring, but if you go on these if you cross these caustic lines, you get magnification. And if you're very close to the line, you can get essentially infinite magnification on the line, but on either side you get the very high magnification. And so you can do that. You go through the cusp, you can do that. If you go through the core, there's these various other kinds of things. So these regions are the large time delay, intermediate time delay, and short time delays, depending on what's going on. So now you can look, this is just to remind you of lensing. Here's the caustic and so forth. Here's a source traveling in to where one's going to be right where the Einstein ring is, but you get an Einstein cross with an elliptic, right? But when you're on this caustic, the green one, you see you get this big, huge magnification, right? And so it's crossing the caustics where you get the huge magnification, but the second one doesn't have nearly the magnification. It's the relative areas that tell you, but you can set up situations where where you're crossing the right place, and you'll get two caustics that are close to you. When you cross the caustic, you'll get them close together. This is also, this particular kind of lensing is one of the places where the new data coming in that's going to push the limit on primordial black holes down to the 10 to the minus 3 of the dark matter, because they can't be more common than ordinary stars by a significant factor. The ordinary massive stars also make these caustics have wiggles and little crosses and pluses in them and so forth. So you can actually observe that and see them change, and you would see them change differently if there were a lot of primordial black holes. Okay, so this is that kind of example. Here's another example from an old thing that Roger did. But this is the closest one I could find quickly to show what happens when you get on a caustic and what kind of images you get, what sort of things you can, how you can get really huge magnifications or how you can get other things. So crossing in the upper section gives you these images. Crossing at the cusp gives you these other, you get these various kinds of things. Okay, so now we go back and look at the time delay with the legends. Depending on what branch you're on, whether you're going to a cusp. So if you cross the cusp, you have a time delay that's in the order of 3 years, or the other cusp, a time delay that's on the order of 20 years, that kind of time scale. However, on this upper branch, you can get down to where you're on time delays on the scale of a day. And the question is, what's the relative magnification of the two images? And that's the part that still has to be worked out, although you can see there's a huge scatter, right? If you're looking, this is just a grid sampling going across the grid and calculating. There's a huge spread in the delay from, tens of days down to a tenth of a day in terms of what the time delay might be. Okay. All right, and so this is not so unusual. Here's a paper by Ogure, Suto, and Ed Turner on the time delay distribution for just the supernova, right? They were worried about supernova at redshift of 1 and 2, and they did the probability calculations of what are the time delays between the images based on the separation of the images and so forth. And they're getting similar kind of answers, although they have it in years here. So they're getting similar kind of answers to the kind of time delay that I'm calculating and so forth. Jose Maria is running the code, we can see. Okay, so let's see how I'm doing for time. It's time. Okay, so good. Conclusions. It would be, when you go through the numbers, it would be extremely surprising if, given the strain limited detections from LIGO Virgo, and given the configurations they have, that they don't have at least 10% gravitationally lensed events. Our argument is, it's quite possible that could be boosted to 50% if everything fell right. But it'll be very surprising. And even when LIGO upgrades, it should still get 10% these gravitationally lensed events. Okay, if the source of the binary black holes has a similar mass distribution to the galactic binaries, then these things will show up as having higher masses because they come from a great cosmological distance, and you don't have the 1 plus z factor taken into account, right? And if the parent black hole mass distribution is narrow and there's strong evolution of such binaries, then half the detected events could be from there. And then that's what we're claiming is the most consistent of the scenarios that I gave to you for explaining why LIGO has these heavy mass events. Now, you can also say it is physically possible to make 30 solar mass black holes out of stars. It's just a question of likelihood. It's how much you have to push the parameters, how do you have to do to get their stuff together. All right, so anyway, we can predict that you can test this, that future observations should see a similar distortion. If LIGO were to go back and look at all the events that are 2 sigma below the 10 sigma threshold, there should be a distribution of them. They should show some noise or some extra stuff in it, but there should be a lot of them out towards the place where the stellar mass distribution peaks, right? There's a certain threshold which will show up. And then there should be some lensed events that didn't quite make it, standing off the end and looking to be at a higher distance. You can predict those. You can predict a set of things about how the existing data should have some events in it, but you can make predictions about how to look for more stuff in the future. And if LIGO were fully successful and got upgraded to a very high level so it could see to a redshift of 1, then you do not gain that huge factor and lensing becomes less important factor. But as long as LIGO is below a redshift of like 0.2, it's still going to have significant lensing. Okay, so I'll stop here. Okay, Roger. Start with the hard stuff.
I mean, it's interesting. I guess the thing I don't understand is why you're claiming that the existing gravitational radiation black hole events are lensed.
I'm claiming half of them are lensed.
Half are lensed.
And half are not very lensed, not very little lensed.
Yeah, but if you're at their high magnification, then generally there's more than one image.
Yes.
And you've gone through a calculation of the time delays, but why haven't LIGO Virgo seen repeat images already?
All right. So the answer to that is you have to think about it for a minute. It depends on how long they run for and what the actual time delay is. Remember, I had this plot that showed you it has to be in this upper. To get those, 100 magnifications of 100, I have 3 places I can cross. The most likely place is in that, along that upper line. That upper branch still is the only one that has short enough time delay that LIGO could have seen it. Because if it went through either of the 4 cusps, those time delays are too long, right? So it's only this upper branch, right? Now the odds are more likely to go through the upper branch, but even there, it has a time period between 1/10 of a day and tens of days between these kind of things. So that's the first thing. The question then is, what's the relative magnification of these things? Remember, these guys got a signal to noise of 8 or 10. I can't remember. This one event is 30 or something like that, right? I can't remember. But if you have a significant demagnification and you only had the 2 LIGO things on, there's a quadrupole dependence of the antenna. Depends on where it is, depends on whether they're both on the air, and so forth. And so, LIGO has been extremely lucky. They should have seen one of the 3, perhaps. It's not clear, but with only 3 events, you don't know. It's a little hard to tell. And they might have some stuff sitting there, just down into the candidate level or just at the edge of the noise level that could be these, and you could do a joint fit between them and look for it. And so, you did some stuff on lensing. Think about what the difference in the magnitudes are. I mean, I showed you one example on the cusp where it's the ratio of the area is like a 10, right? And if it's 10 times less signal, you just aren't going to see it in LIGO.
I don't think that's, I mean, if you've got large magnification,
Then they
the two
should
images
be
have the same,
very close.
most of the cross sections associated with fold lines, and,
Exactly.
and
Yeah.
asymptotically they're the same,
Right.
and the magnification should be the same. And I agree that there could be a duty cycle effect, but it seems you'd have to be terribly unlucky not to have seen one of these.
With 3 events, one of which is not really super high single noise, but 2 are high single noise, you have to miss them somehow.
Yeah, well,
All
okay,
right,
that's
so
like
David
a
will
strong,
say something.
Strong prediction going forward at any rate.
Yes, exactly.
Yeah.
No, this the good thing about this model is we can be proven wrong in less than 100 years. We probably can be proven wrong in a year or 2.
The old slogan in the quasar business is no magnification without multiplication.
Right. Well, one of the things that we've known, right, is that in fact, if you look at the luminosity functions, that up to a certain point, it's unlensed, and then you see a tail that's lensed, right? So it's a question. It has to do with where the magnitude limiting. I mean, LIGO is just in a situation where the magnitude limiting is big, and the selection is big, and the volume they're surveying is small compared to the cosmological volume. Whereas with quasars, it's not quite the same ball game, right?
But 2 more questions over there.
Well, no, he was going to tell you why they missed it.
What I was going to say is that if there were a lensed event that had a time delay, and that was say 10 days or something, it would also have a different amplitude, and so it would be identified as a different event. It wouldn't be identified as the companion lensed event. So you don't have the achromaticity that you have for quasars and things to be able to show that those lensed things are actually the same object.
Right. But they should come from the same, they should be intersecting circles on the sky.
Yeah, but the angular resolution is so bad that that will...
Right.
You won't be able
I
to
didn't
tell.
spend much time on it, but this tells you very much want to have more detectors online, because you can work out the angles. That error bar that's so wide and distance, you can shrink that very substantially. You still don't have the magnification, or not have the, but you can tie many of these things down more, and you can get the angle much better, so that if there's an imaged event, you will be able to say, yes, this is an imaged event, right?
Again, the galaxy lenses at high magnification, the time delays get very short.
Well,
You know,
yeah.
well, anyway.
Well,
There is one more issue here, which is
Just one?
yeah, no, which is usually neglected, but it's important. It's the fact that the black holes seems to be not spinning, in the sense that the total angular momentum of the system is small, and if you push the origin of the merger to earlier time, you would expect the spins to be higher. So there is a contradiction here between the solution of having of observing much younger systems. I mean, systems that have emerged actually at higher redshift, with the fact that we observe them with all the systems that have been observed were effectively non-rotating. The black holes were effectively non-rotating before they merged. So this just makes this problem slightly more complicated.
Yes, you're right, but it's not overwhelming data. It's like, you would expect in almost any binary system, if there's any mass flow or anything else, that they would spin up, but maybe not, right? It's hard to say, and so I don't know. I mean, the problem is we made this whole model, and there's only 6 events, and only 3 of them are lensed, right? In our model, right? That's not high statistics, right? But we do make definite predictions. We do think that when LIGO turns on again, the LIGO Virgo turns on again, they should be very quickly able to do some of these tests to see whether this is a reasonable model or not. And, you know, it falls into the tradition of astronomy. The selection effects turn out to be very important, right? But so this is a proposed model. If it is correct, it means that LIGO has to come up with more detectors and more schemes to actually measure the redshifts of these things. And in order to do that, David, so I'm giving advertising for the next talk, you need much higher angular resolution so you can search the galaxies looking to see where the source could have been, and then you can follow up on it. But if you don't have some independent indicator of the redshift, you're always open to that. And then if you want to measure the Hubble expansion rate, you have to take enough data to see that you have a nice distribution. You know, there's the lens guys, and then there's the unlensed guys giving you the information.
In your paper and in the first part of slide, you showed the optical depth of the lensing is 10 to minus 4 or something
Right,
like that.
for magnification greater than 10,
yeah.
but for greater than 100, it's 10 to minus 6 almost.
But you are considering the highly magnified cases.
Exactly,
So the
yeah.
optical depth
I had to
should be
ease you guys
smaller.
in.
Should be smaller.
Yes.
But in the final slide, you showed the 10% probability of the lensing.
10% of the
Why this?
10% of the events, not
Yeah.
that 10% chance of lensing, 10% of the events that LIGO publishes, or LIGO Virgo publishes, will be lensed events. Not that 10% of the events, it's only 10 to the minus 6 are going to be lensed that greatly, but there's a lot of them. There's a huge number of things out at redshift of 1 and 2 that can end up being lensed and going there.
So, but optical depth is a probability, essentially.
Yes.
So why 10 to minus 4, 5 or
10
so
minus 4,
becomes
10 minus 5, 10 minus 6 for these guys.
0.1 just.
Yeah.
Why?
Right, no, it's just because you have so many more sources to be potentially lensed, and you do not see the sources that are not lensed. You only see the ones that are lensed. So you don't see, 100% minus 10 to the minus 5 you don't see, right? It's only the 10 to the minus 5 you see.
Mm-hmm. So you are considering not the original lens, but the cusp or something like
The
that.
ones that, yeah, it's because they're magnitude selecting that the strain at the Earth has to be bigger than the 10 to the minus 21 or 10 to the minus 22, something like that.
Right. I think in view of the time,
Okay.
let's adjourn this discussion, and presumably you can still ask George later on.